Hello. So what I'd like to do here is just go over pi as a number. And pi is no different than any other number, 1 or 2 or 3. All pi is just like any other number, is a representation of a concept. It has no real value in and of itself. These are all to help us conceptualize different things, because we make all the definitions. For example, we define what a circle is. A circle has to be a center point, and every point is equidistant from the center point. Now you can see that this circle is not even like perfectly equidistant. It kind of like waves in here, and it's not 100% perfectly circular. It's got a little irregularities. So is this a circle still? Well, in mathematical definitions, it would not be a circle, because if I did the ratio of this to the diameter of 1, I wouldn't get exactly pi. I would get something a little bit less or a little bit more, depending on how wavy it was relative to the perfect radius that it's supposed to be equidistant by a radius around the circle. So a circle is even a concept. These are all definitions that we made. I would still call this a circle, even though mathematically it doesn't fit the criteria for a perfect circle, because there is not perfect radius. It looks like it waves in a little bit here. So the radius would be shorter here as it is here. Or the diameter. Another definition, a diameter across the fattest part of the circle. We could call this a hemidiameter across the halfway point between the apex and the diameter. These are all definitions that we made up. It just happens to look nice because it's in the fattest part. But I could call anything on this thing. I didn't have to call it a circle, etc. I think you get the point. This is a language. So let's look at pi, which is a concept. So pi, when we say pi, we're talking about that pi equals the circumference over the diameter. But what are we talking about when we talk about the number pi? We're really talking about what this number is relative to our unit 1. Because numbers have no meaning unless they're relative to something else. So pi is equal to 3.14 when we consider that it's relative to the number 1, it's equal to that value. If this diameter is 1, then it equals 3.14. If that diameter was 2, then we get 6.282, etc. But the ratio would remain the same, because if we divided 6.282 by 2, then we get 3.141. So pi really equals pi over 1, or approximately 3.141, and that value over 1. So 1 pi equals 1 circumference over 1 diameter. Okay, so we really mean 1 pi, and we mean pi relative to the number 1. That's the point here. And we could rewrite this as 1 circumference equals 1 pi times 1 diameter, or 1 diameter equals 1 circumference over 1 pi. So circles, pies, circumferences, diameters, these radii, these are definitions that we chose when we created the language. I could have called this I don't know, an elephant if I wanted to, instead of radius. Or I could have defined the radius, maybe I said, 2/3 of the distance between here and there is where the center of the circle should be, and I'll call that the center. These are all things, but it looks pretty when it's in the middle. And it looks pretty. We like symmetry, so we're naming these things fattest part and total center and this. That's just because that's the way we wanted our language to be. Again, is this a circle? I still think it is, even though it's a little wavy. I tried my best, but I still call it a circle. So let's look at pi. So if as I said here, pi, when we talk about pi, we mean pi relative to 1. Well, how about pi relative to pi? Well, pi relative to pi is equal to 1, because that's our definition of 1, is complete unity. We've defined 1 as unity. So anything over itself we defined as 1. So you want to make a 1? Well, we can just do this. Or we could put 2 over 2. But pi over pi equals 1. And this over that, these terms in mathematical language cancel out, and we get 1. We get unity. So now I can make another circle, and I could say, okay, I'm going to make the diameter of this circle pi. Okay? So pi over pi equals 1. So 1 pi, we already knew, this is the formula, equals 1 circumference over 1 diameter. I'm going to now multiply both sides by 1 over pi. And I'll get pi over pi equals 1 circumference over 1 diameter times 1 pi. And now I can solve for 1. 1 equals circumference, 1 circumference over 1 diameter pi, or 1 equals circumference over diameter pi. So here's a new definition for the number 1 in terms of these other definitions that we made. Circumference, which is a defined, these are defined. A 1 is a defined. These are all part of the language. Equal means the same as. Circumference, we defined as the distance around the circle. Diameter is the shortest distance, defined as the shortest distance between the thickest parts of the circle. And pi is defined as the number of times the diameter would fit into the circumference, the ratio. That's our definitions. All these are definitions that we made up. It could have been anything under the sun. Elephants, chimpanzees, we can name it whatever we want. Conceptualize whatever we want. We like the centers, we like round things. So we made all our language based upon these perfect things. And that's the language we made. So when we solve for 1, so we have 1 equals circumference over diameter times pi. So 1 circumference equals pi times the diameter. Okay, but in our case here, the diameter is pi because we're using this new circle. So that means 1 circumference, when the diameter is pi, then the circumference of the circle, which I label here, will then be pi squared. So for a diameter of pi, the circumference of the circle will be a pi squared. So pi equals circumference over the diameter. Circumference over diameter, that's our definition of pi. So pi equals, in this case, circumference is pi squared over pi, and then pi equals pi, which is pretty much getting back our definition again. So here we have our new value of 1, which is 1 equals circumference over diameter pi. We could also say that 1 equals that in relation to pi. Because numbers have no real meaning in and of themselves. They're symbols to represent things. And then when we give these symbols, we have always to say, well, what's the symbol relative to? Well, pi, when we talk about 3.141, we're really saying pi relative to our number 1. And here, I'm going to say, okay, let's do pi relative to itself, pi. Well, now, that's what it equals to. So pi relative to pi equals 1, and pi relative to 1 equals pi. So numbers have to be relative to each other. Here I'll do relative to x. So pi relative, I'll multiply both sides by x. Basically whatever's in denominator is relative to. That's kind of our language. So pi relative to x equals circumference over diameter times x. So let's say in this case we'll make x equal 1.397. Of course, when I say 1.397, I mean relative to number 1 when I speak of this number. I could say that this number is relative to 1/2, and then it'll double as 2.6, whatever. But when we write out a number just by itself, we really are saying the number divided by 1, because anything divided by this unit, which defines mathematics, is a unit, we get back the number. So over here, when I say that number, I mean that number relative to 1. So then equals circumference times diameter, x. I'm just using this formula, which is the pi formula. And then basically we get our circumference of 1.397 pi and the diameter of 1.397, where pi is that ratio that we talked about. And the definition of pi is based upon a perfect circle with the radius, a perfect circle with the diameter, because we're talking about pi, exactly through the fattest part. So if we take that ratio of that and we do it to the circumference, we get pi. And in this case, of course, I mean pi relative to the number 1. So we could do the same thing as like the square root of 2, which uses, it's another thing. So a square root of 2, well, the right triangle rule with the Pythagorean theorem, and again, these are just concepts and symbols, and but using the language, when we talk about the square root of 2 being the hypotenuse, we mean relative to 1. And we mean 1 relative to 1 and 1 relative to 1. Because for a square, for a triangle with right angles, we have a squared plus b squared, like this side plus that side, equals the hypotenuse squared. This, and this. Famous equation. This is a, this is b, this is c. So if we do 1 squared, or 1 over 1 squared plus 1 over 1 squared, would be 1 plus 1, which is 2, equals c squared. We solve for c, we take the square root of both sides, and we get square root of 2, relative to 1. But now let's look at it relative to square root of 2. Because we could have just made another number, because 1 really means unity. So I'm going to say, okay, square root of 2 over square root of 2 equals 1. I'll make this side now square root of 2 over square root of 2. And then we'll do 1 over square root of 2 and 1 over square root of 2. So I divide all terms by square root over 2, because now I'm saying instead of the numbers being relative to the number 1, I'm saying now, oh, well, let's define a new unit for our language right now. And we're going to say it's all relative to this. Okay, so then let's do the same thing. We get this term squared, and this term squared equals this term squared. So I get 1/2 plus 1/2 equals, and this, I didn't carry it out. I think it's faintly there, but it should be 2 over 2, which then becomes 1, right? Square root of 2 squared is 2 over square root of 2 squared is 2, and that becomes 2 over 2, and it becomes 1. So 1/2 plus 1/2 equals 1. 1 equals 1. So anytime we write a number, we're actually saying, without anything under it, we mean that it's relative to 1, because we're defining 1 as our unit in mathematics. So when we write out a number, we really mean relative to 1, unless otherwise specified. And then we can have these other things where we could say, well, relative to pi relative to itself is 1. Pi relative to just 1 is this number, or close to that number, or pi. Mathematics is all relative. In summary, numbers have no reality. This is all stuff that we made up, all symbols to represent things. They don't have any real meaning in and of themselves. They're shorthands to convey concepts. They're definitions, circles, squares, rectangles. We made up these definitions. Everything in math is all made up by us to help us do things that we do in the real world. Everything in math has to be relative to another thing, since like the size of something. In other words, the number has to be relative to our standard unit. Otherwise, it makes no sense. If I put pi over 0, in mathematics, that becomes undefined in the language. And you can go back to my other lectures to see why that's true and why the language breaks down sometimes. But, we could put pi over 2. So pi relative to 2, this is just a number, relative to 2 is that number. It's different than that, and it's different than pi over 1, it's different than pi over pi. Pi over 2 is something else. So it's relative to other things. Same things with locations. You have to say, well, I move this far relative to this point. Otherwise, if I just say I move this far, and I don't tell you how far relative to whatever, if we're, distance has to be relative to something else. Otherwise, we don't know. That's why we have scales and maps. Like this could mean 1 mile, or on a different map, this distance can mean a million miles, depending on the size of our map. The distances in and of themselves are meaningless unless it's relative to something else. So everything's defined, and everything's relative. We also, like I said, define what shapes are. Mathematically, the radius is equidistance from the center at all points. That's the mathematical definition of the circle. And so for all of these circles, that'll be the same, and therefore the ratio, the pi, will work out for any circle when we use these defined definitions. And like I said before, well, is this a circle? It's got a little bump to it. Well, when I do the calculation, this is going to be a little bit more than 1 radius. And this will be the radius. So what's this? Well, this won't come out to exactly pi anymore. It's going to be a little bit greater because it's a little more than a circle. It still kind of looks like a circle. I don't know. This one, is it a circle? Well, mathematically, it doesn't fit the definition, so it's not a perfect circle in our language. But to make our rules and everything, we said, look, if we're going to make these rules with pi and this and that, we're going to make perfect circles, and we're going to do it like that. So our math is consistent, and it works, and we agree upon it. And that's what it is. It's a language that's agreed upon. Maybe, someday someone will say that this is a new circle, that halfway around I'll do a radius, and then when I get to the halfway point, then I'll change it over to a diameter, and we'll call this a circumelliptical something. I don't know. But that's up to us. So I think that's kind of what we got to say here, that math is a language, and that's what it is. And we can define it the way we want, and we use it the way we want, and it's a useful tool. But to look at these numbers and say that this number is something special about it, it's no more special than any other number. It's just that we wanted a perfect circle, and we wanted to describe something relative to if we have a diameter with a distance of 1, what this symbol is going to come out to, given all the definitions of what a circle is, where a diameter could be drawn, etc. That's what this number is. But I mean, maybe this is a special number to somebody else. That D and R, and using a little bit of maybe this circle is more beautiful in other cultures. They don't like pretty things, and so they make a new pi that has a different value because it's not perfect. So that's it. Nothing more special about anything else. The language is saying what the language was built to say. And thank you. And we'll see you at the next lecture.